Hello everyone, and welcome to this video short where we are going to introduce the tree data structure. Trees are an integral and fundamental data structure used in computer science with all sorts of data science applications. Two clear applications of trees are number one, a data structure, simply meaning to store and organize data. Number two, trees can also be used to illustrate and diagram out a flow of a process. A great example of this is a decision tree, a classifier that is used often in data science applications. The goal for this module and a few subsequent modules is to overview trees, identify some of these applications, and then go into some greater details with specific types of trees. But first, we'll go over some of the basics. And we'll have to take a step back to talk about some fundamentals with respect to memory and memory allocation on a computer. Previously, we discussed arrays and contiguous allocation. It is often the case when implementing a tree, however, we will use discontinuous allocation of memory on the machine. This will allow for a more flexible data structure that can increase and decrease in size dynamically, that is, as the program runs. In order to do this, we will need to implement a tree as a linked list rather than an array. There are some types of trees, however, I should note, and we will discuss later on, that are often implemented contiguously as an array. All right, so let's talk about linked lists. So how can we store a list of items discontiguously on a computer? Contiguously makes sense, right? We can just simply go to the first item, and then the second item, and the third, and continue on in that manner. If it's discontiguous across chunks of memory in the machine, however, it's unclear where the first item might be and then where the second item might be, as they might not be adjacent or even near to each other in memory, right? Thus, the linked list. So how does this work? Well, a linked list is a composite data structure, which number one will store some data items, and then number two will store a pointer, right? Essentially, the memory address of where the next item in the list is located in the machine. This allows us to, in a sense, chain out our list, even though the data is not stored contiguously in memory. Right? We have supplied that extra pointer that completes or connects the chain, the list of items to be stored. If we were to implement this in Python, the class definition would look something like this. Again, where we have at least two data members, one data, the data that we're going to store, and then number two, a pointer to the next node in the chain, the next item in the list. It's that simple. All right, now it's important to note that when implementing these classes, you always want to abide by good programming techniques and best practices. And so always make sure to do that and use doc strings. Comments are good, yes. All right, so why do we mention linked lists here? Well, I'm going to jump ahead to the discussion of trees, because trees are often implemented as linked lists, as I noted. All right, so first, a few definitions related to trees, and we'll go over some of the fundamentals. So, trees are composed of nodes and edges. All right, so what are nodes and edges? Nodes are often illustrated as circles or ovals in a diagram, and edges are often illustrated as lines or arrows. The nodes represent nodes very much like a linked list node, which are going to store some sort of data or some sort of object. Right? Edges indicate relationships shared between these nodes. So here come the definitions. All right, so there is one node that is often labeled or designated as the root node. Right? This node is often the node drawn at the top of the diagram. Right? And you're thinking, well, why is that called the root? Well, you can think of this tree as an inverted tree, right? Because the root is up here on top and the leaves are down here on the bottom. Right? We can identify the leaf nodes because there's no out arrows coming out of them. And we can identify the root node because there's no in arrows going into the root node. All right. These leaf nodes are often referred to as terminal nodes because they have no children. That is, there are no nodes connected below them. Internal nodes are nodes that are nodes with children, right, that are not the root node. Right? The degree of a particular node is the number of children that it has. All right. Again, edges are the arrows or lines connecting the nodes, and they represent some sort of relationship here. In a very generic and general sense, the relationship shared here is between parent and child node. So, what does that mean? Well, the parents are simply illustrated above the children in the node directly. So you can almost think like a family tree here, where we have a parent and a child relationship. So A is the parent of C, and C is the child of A. And A is the child of R, and R is the parent of A, and so on and so forth. Note here that we've identified the height of this tree as being 3. I should note that in some literature, the height is counting the number of edges from a root to the leaf node that is maximum, and not the number of nodes. So here, we're clearly counting the number of nodes from the path, right, following this sequence of edges from the root node to a leaf node. Right? So if we're counting nodes here, we get a height of 3. However, as I note, in some literature, the count of that height would be 2 if you're counting the number of edges. It's always best to simply clarify how you are counting the height in terms of nodes or in terms of the edges. Now, when we refer to the height, it's the longest path from root to a leaf node. So in this particular example, note that we jump 1, 2, 3 to get down from this root to this leaf. And if we go down this way, 1, 2, right? We only jump down 2 edges. So here we would take the maximum of all of those such paths or routes from any node to another, here the root node to a leaf node. We see that the maximum distance or the maximum length path from a root node to a leaf node is going to be 3. 1, 2, 3, if we're counting the edges. So the height of this tree would be 3 if we're counting the edges, and the height of this tree would be 2 if we're counting the edges. All right, just to clarify. So why are we studying trees? Again, trees are integral data structures in computer science. They're great for organizing data. They're very flexible, they're dynamic, and they allow for improved times when it comes to storage and retrieval of data. They're also great for mapping out the flow of processes, algorithms, and things such as classifiers. So I encourage you to read on in this PowerPoint slide and learn a little bit more about trees. Again, focus in on some of the definitions and the details related to these trees, as we are going to use them throughout this module and subsequent modules. All right, thank you for joining me in this video short, and I'll see you next time.